Okay, we are back onto the workshop, to the afternoon session of the geometry, hierarchical geometry workshop. Um, so we continue to do what we are doing in the morning session. So let me share my screen. So to remind you, we were working on, or we are just checking the agent algorithm, specifically called clock stack agent algorithm. And we are following this tutorial page on ijo.jp. And then, so we went through some of the code and explaining the meaning and the methods of the agent. And then we continue to do that. So we were somewhere around here. I think we finish, or I finish explaining this part. One thing is that in the morning session, I could make one of the example work, and then I found the reason of the problem, which was so I was making the rotating agent, we creating arc, and then but every 10th time frame create 90-degree turn, then creating kind of a pentagon like rotating shape. And then I was trying to put another level to it, but you didn't see that another level. That was because my change in the another level was too subtle and nothing you can really see. So if I changed up more with rotation, so it was happening, but you didn't see, or it was just tiny change. So if I change that, it's a bigger move, like a 0.9 pi rotation. Yeah, which is like close to 180 or 160 degree turn, which makes that turn. So, but anyway, so that clear. So that's the third level body clock move or behavior. So first level was this slight arc, and the second level was this kind of pentagon-like turn, and then third level was this another turn to make this pentagon almost flower petal shape like module, then going on. So, but anyway, so that was so this kind of way of adding code. So like a first level, I was just doing this rotation code is pi divided by 100, and but I added a first clock, first kind of level of behavior using the body clock 0, and then I added another level with the body clock 1 as a higher level of behavior. So, but anyway, so that kind of keeps putting on top of each other. It's kind of kind of a regular way to develop this algorithm. I mean, this type of algorithm. So, but anyway, I keep explaining other examples. Now, I actually in the tutorial page, I'm doing the kind of step-by-step agent or hierarchical agent building by starting with, I mean, it doesn't show here, but first one is just straight line, and the straight line is turned into square, and then square becomes a sequence of square, and then the sequence of square is turning into square of sequence of square, and then that also becomes sequence of square, and then next is this. So one more step to it to add. Actually, let me let me just remind you that how many level we played with in the previous step, and then I'm gonna compare that to the next level in the next code. So right now, well, actually, this one. So sequence of square was made out of um, so body clock 1, 2, and 3. Actually, no, 0 and 1 and 2 was used to check the function. And then also in the end of the first part, body clock 3, which is the fourth level of body clock, was increased, and then that is responded by here. Body when the clock 3 is changing, you do another thing. So then that this body clock 4, so body clock level, so 0 and 1 and 2 and 3 and 4 is appearing. And but body clock 4 is not really show or used in the clock method because this is the part which resets everything. So when the higher clock is set, or just increasing by 1, all other clock below that is reset to 0. So this highest level body clock is functioning as just reset whole thing, then we start from there. So in this case, that happens the end of here. Uh, I'm not sure if the math cursor is shown, but that end of, let me keep opening chat in case somebody asks anything. So uh, like a branching point of first square of sequence of square, that is the part or the clock is reset to 0 except fourth level, and then we start drawing the square of sequence of square. So that's the moment. So basically, whatever biggest number of clock you tick, that resets everything, and that restart your behavior restarts from there again. So that what agent is doing so far is repeated if you set the highest clock so far. Then that was the previous one, and then now I want to show you next one. The next one seems to be more going two-dimensional, and then kind of want to first just to compare between this copy and paste code to the tutorial code on the web. You see the last time the 4 was the largest number it shows up, but in the clock comparison in if condition, number 3 was the biggest number to compare. Now next one use another level, which is 4. Clock level 4 is used for comparison, and they also you see the clock 5 is um, ticked to reset whole thing, to restart whole thing. So, but there's 3 conditions, 3 cases of that happens, the reset of whole thing happens in the level clock 4. So then let me copy and paste this one and run. I should just copy whole thing. Then replace all the rule. So now I'm gonna take a while to start. Now it's but as you can see on the image, it's supposed to create this 2D grid out of sequence of square. Square. So it's supposed to turn. I think that somebody is turning 90 degree again. Also, it's not like 3 branches. Or actually, this part looks like 3 branches. So first, the sequence of square of square of sequence square. So now it's kind of branching to 3. branching into three. So this straight one, and then left one, and the right one. I think that's a basic behavior. So it's either keep going straight, or it goes left, or it goes right. But they turn in a very specific location. I kind of lost which was the first one. But anyway, assuming this is turn. So, but the three turns are not necessarily turn at the same point, because this, let me just focus on the, or let me use annotation to. So here is the location. Okay, I couldn't precisely write. So here is the location when it goes straight to next sequence of square. And then, but this is not the position where it branches into three. If it goes, it would collide into each other. This is one, but another is actually happening from here. Going up is happening here in a different square. And then third one going right is happening, I guess, here. So the code, I want to stop drawing. So the code in the processing is describing that three. Okay, I cannot do the results here, but in that case, what I can do is I can move the code. So I have three conditions, and clock two. Actually, I should read from the higher clock. So clock 3 is 0, meaning clock 0 is the edge, clock 2 is the number of edge, and clock 1 is the number of edge, and clock 2 is the number of square. Clock 3 is number of sequence of square. So clock 3, 0, meaning, I guess, first square here. Is that right? But anyway, so clock 3 is 0. Clock 1 is 2. Yeah, that level I already start confused. So clock 3 is 0. Okay, again, clock 0 is a straight line, and the end of the clock 1. And clock second edge, first square, first sequence. First sequence is this. Okay. I think the first one might be this one. So first sequence of square, and the first square, which is this. Okay, I should write it down. Okay. Is different color. So now, so first sequence, clock 3 equals 0 means the first sequence. Okay, now first sequence is this. This might be basic. First, so that's a clock 3 equal 0 part. And then out of first sequence, first square is this, which is clock number 2 equals 0. And then inside the square, there is a first edge, second edge, third edge. So third edge is this part. Third edge needs to be 0, 1, 2, and the third one, so which is, this. So this is here. And the second one is from clock 3. And second sequence of squares. So second sequence of squares here. That's a clock 3 equal 1, meaning, and then out of that sequence, clock 2 equals 0 means the first square. First square is this. And then on that in square, clock 1 equal 2 means the 0, 1, 2, so third edges, third edge. So first, second, third, so that's this. So this one, this term is this part. And the last one, sequence number 2, meaning 0, 1, 2. So third sequence of square, which is this one. And out of the clock 2 equals 0. That means the first square out of that. First square. And then clock 1 equal to mean the third edge on the square, which is here. And this goes to, wait, what? Yeah, that term is the third line. So that's how it works in a way. Although that's kind of post-analysis, and then that's not necessarily how you start thinking in the beginning. And it's more like, in this case, I knew I wanted to make a grid, and then that made it, well, actually, I kind of struggled to do this to figure out. So I tried many things, and then, like, it turned out this was the one way I could do. So at that point, I was right. I mean, if I knew I wanted to make this specific grid, and when I draw a diagram, it's understanding which clock is what, and then in this way, and then, okay, this is the second one, and the clock should be set as number 2, clock 2 is 0, and the clock 3 is 1, etc. Then figure out which numbers go there. So, I mean, you can do that too. So, but as I mentioned before, when you do design exploration, it's faster or more dynamic if you just simply play with number, meaning not knowing what it does, just keep changing. That usually is quicker and better and interesting. So, but if you want, but that's one thing for your project. But for you to understand, sometimes it's good to sit down and draw diagram and then try to understand what's where. So anyway, that's this example. So let me clean up this drawing first and then move on to next tutorial. Then, so next one would be on the website. I think this is just a variation, angle changed version of the previous one, I guess. Let me check. So let me run this. And but yeah, when I copy and paste, it didn't change much much on the lines, and then line number same is kind of if else structure is same. So I think the major difference, or the only difference would be this angle, like minus 60-degree turn, or I suppose minus 60-degree turn. So that's logical structure is exactly the same. Only the turning angle is different, and then that creates different grid. So it changes from orthogonal grid to triangular grid, but it's still made out of sequence of square, a sequence of square of sequence of square. So, but that's another level of control, right? So it's a structure. I mean, developing the logical structure is one thing, which is actually usually trickier. And then adjusting parameter is another thing, especially like a scaling or rotation. So then to get certain design result. So, but usually the structure has bigger impact, and then parameter has minor impact, and then I mean, you see the resemblance from this grid to the previous grid. I mean, you can understand that. So uh, that's the kind of level of change. And then another thing is that because this whole agent, actually whole agent is making module out of other module, actually, but they are all made out of same agent, which is just short line. So because of that, when they collide into somewhere, or itself collide into, I mean, same agent, they still maintain partial module, meaning, or as much as possible, because module, this like a square of square, or square of square module is not the base module of this agent system. The base module of this agent is micro module of just line. This one edge is made out of 9-line agent. So that's another kind of adaptive behavior in a way. So then still like a collision detection algorithm is applied everywhere. So when they collide, they stop. I mean, you can turn off the behavior as well. But that's another idea. Like if you actually, that's another kind of thought behind this algorithm, that if you like, I'm kind of assume the discussion of a discrete module approach, that it's better kind of to maintain certain rationality in design. It's better starting with a module or discrete module system, and that's true and true for construction. But I kind of didn't want to give up the adaptability of agent system, so I wanted to build module made out of module agent. So I didn't want to make a big static top-down module and repeat. Of course, I mean, discrete design people, they use a tiny module as well. But I wanted to do kind of more adaptive stuff. So anyway, so one module made out of other module, and then but it's also true that this agent cannot, or this module system cannot go below the micro module of line. So that's kind of limit in a way. So if you build bigger module out of that, yeah, it has a higher adaptability. So code is complex. But anyway, also joking. And so this is the kind of readjustment or parameter adjustment of a grid system into hexagonal or triangular grid. And but if you see that if you are kind of start adjusting something to explore your design option, you might wonder what else you can change, or I can go there. Okay, before going to the one on the example, I mean, just a simple change. What if, okay, I changed the 90-degree turn on the 3 different location, and what if I change like a whatever random number? This part I doing that without thinking too much. Usually that ends up getting something interesting or something colliding each other and nothing happened. But so yeah, just trying to see. The structure of logic is rational, but angle is kind of irrational. I didn't put any 90-degree other than the base, like a 4 module level. The 5th level is irregular, although that's 45-degree and 60-degree, and then I mean divided by 7, a bit irregular. So just just example of a kind of design iteration or study. So that part is fine, still all regular part, but okay, some of the angles start becoming irregular, but I'm curious what happens as a whole. Yeah, it doesn't look too bad. I mean, I still have like 45-degree and 30, no, actually 60 degrees, so it's kind of several 40-degree turn will come back 90, okay, two 45-degree turn become 90, and then 60 degrees, three of them come back like 180, so it's not that irrational, but I don't know what the effect of pi divided by 7, but plus it's start becoming some of the earlier branching example from yesterday, so the kind of splitting in a radial way. So that's becoming more biomimicry looking branching behavior because of this angle arrangement. So, but that's one effect. So each of them made out of regular squares. But anyway, so those are kind of process, typical process how you explore your design. So then to go to next example, I'm gonna save this code and I'm gonna rename this code in case I want to save the next one. So next one, it's a kind of same thought process. Still, I keep the logical structure same. It's still grid of sequence of square of sequence of square. And in this case, first, actually, so I didn't change the 90-degree turning angle of right in the previous one. So going back to this one. So this part is same from here to here, 90-degree turn in the three different locations. But this code has different turning angle here. So this is pi divided by 180. I don't know why I kept this much by one. I don't need. So this one is so this is the location. Well, okay, I missed one parenthesis. So location is level 0. So this behavior has a clock level 4 to 0. I mean 0, 1, 2, 3, 4. Level 4 is the location of the turning behavior in the big 90-degree turn. That's kept same. And the other part of like a square making part or sequence part, and then square with sequence of square part. Those 90-degree kept same. So there's a 90-degree here and 90-degree here, 90-degree here. But the very bottom part, this was supposed to go straight for 9 times. Is it 9 times? Actually, no, this is now 3 times. I think I changed. 3 times. And it was, yeah, so it was originally going straight, but now it's turning in the lowest level behavior. So it was always going straight to make the base edges, but now that base edge is always slightly turning, and then with the same logical structure, but that causes bending in a way which influences everywhere. So let me see how it comes out. Still running. So that. So first of all, this square is a slightly bend, so it's bending inward a little bit, but that makes the square. Okay, first of all, the effect of turning in one small square is tiny, but the sequence of square has bigger impact, and then that sequence of square couldn't make square of sequence of square. It make like more pentagon shape, And then the bigger one, bigger grid building part has bigger impact, and it almost makes circle. So let me annotate. So this part, this circle was originally straight. So in agents or higher level agents mind, they think they are still making, I'm just going up straight. But because of the bottom agent is not going straight, that influence the whole behavior in this way, and then it goes back this way and collide into other part. So that's what's happening. And let me delete that drawing. So then as a whole, yeah, it's still, so you can see still kind of look like, you still see the regularity there. You still see the grid, but different type of grid. It's circular, or it has certain sensitivity resembling a Middle Eastern arabesque pattern, which I'm not, I don't know why. I mean, you could analyze why, but so, but that was just because of the lowest level agent is time. So, I mean, usually the change of behavior in the lowest level has bigger impact to higher level, or just the whole arrangement or layout of agent. So that's what happened there. But anyway, so again, the you can understand the difference and also similarity between them. There's something same logically, like number of connections always same. How they turn at the local point is always same, but the whole thing is different. And then bottom behavior is slightly different. So that's the kind of effect of change of transformation in lower level. Okay, then now next example. So next one, I think next one will be this is I think another change of angle. I think this might be tamer than before, although not sure. Let me run this code. So difference grants is this part seems the same, 90-degree turn in the highest level, look like same, and this part seems the same. Even this part looks same. And no, actually this is different. So previously that was multiplying 1. So this line is actually going back a bit. So previous, the lowest level turning was 180 of pi, but this is 1/10 of that. So this is actually going back to original grid. And you can see that. You can see this is getting closer to original orthogonal grid made out of squares. And but you also see bending, and then you can also see the effect of micro module adapting the condition. They're still trying to make as much as possible of the module. So yeah, it has more collision or weird collision or half module condition. So but anyway, so that's just a range of change between these two, this circular pattern to orthogonal grid. So it was all controlled by only this angle. If so, you might wonder what else can it do. Let me see, I'm not sure. So Smaller. If I make it smaller, yeah, it will just get closer to the original orthogonal grid. And what if I make it bigger? Uh, that might be chaotic. Five times, I don't know. 4 times bigger angle than this circular thing. But this is like it will bend more and more, and it might be like, okay, somehow I'm imagining the scene from Inception, but like turning into, and actually no, it's gonna be more like Doctor Strange, but well, it's gonna improve. But anyway, so it should be coming. So it might be interesting, or it might be just getting into boringly chaos. And that's something else. Okay, so now it turned into something else. Actually, so okay, so a little bit boring. So in this case, it kind of collided into too much, and it couldn't grow out. It didn't create space to grow, so it kind of came like that. So that was logically this still kind of continuous behavior from that bent grid to this. This is just too much bent, meaning there should be some threshold not to collide into each other. Yeah, let me just tell you one more thing. It's possible that's the limit because it's quite closely colliding each other. Um, then of course you can start thinking about, okay, maybe sometime going bending left and sometime bending right. That might be more interesting, etc. That's, you are right, and you can, if you think of that, you should explore that. Then that's the result. Okay, turning is colliding into each other. Growth is actually growing. Yeah, this will just go more the pentagon-like thing, and then circular thing is okay. So it's still colliding each other. So I think that was I mean, the previous one, like just 1 degree turn would be like a limit on of like infinitely growing pattern. But anyway, so that's the range. Then next, I think the next one has a different logical structure. Well, actually, the structure is same, but now this we start think about putting being randomness to it. That's another thing you can think about. So let me copy and paste. But this is just changing one location into random number, which is here. So the 90-degree, the highest level 90-degree turn is here. 3 different 90-degree turn. But that happens only when random integer. So this random method, so inside the IGR's random number class, you saw the method get yesterday, which gives you random number. I mean, but in terms of floating point number, I mean, as floating point number. But there's another method called getInt, which gives you random integer. So it gives you a discrete number. So it's not like 1 or 1.1 or 1.9 something. It's more like a 2 or 3 or 5 or 2 or 3, or you can choose a range. So when you say get int 2, 7 means this method returns some number, either 2 or 3 or 4 or 5 or 6 or 7. That includes the beginning and end of this number. So then that's used for the control of clock 4. So clock 4 is the timing when it branch into the different direction. And then, so that is randomized. So first let me run this code. And then actually I forgot to save the previous one. Anyway, so I mean, you already can see in the image, but clock 4 is actually conceptually, it's a count of big square. Big square is like made out of square, sequence of square, I guess. So, previously it was specific number. So this big square is counted by clock 4, I guess. But sometimes it's 2, sometimes it's 7, sometimes 4. So you can see like previously I think I had like 4 square and the fifth one is turning left, but this one has a third one turning right because this random number checks or sometimes gives you 2. Actually 2 is like, because it starts from 0, 0, 1, 2, and 3 is third one. So this, I think this example in the on the display is case clock 4 equals to 2. So only equal to and then turning here. Then sometimes we equal to again, then turning left, and then but sometimes it goes longer. This is like from 0. I kind of forgot if reset. Yeah, so 0, 1, 2, 3, 4, 5, 6. So in this case, clock 4 times 6, and then 6 and that turn into, well, actually event, it applies this behavior here. So this is a randomness introduced at the highest level. So clock number 4 is currently the highest clock to control. I mean, clock 5 is just used for resetting, so it's not really controlled. So that's the logic. And but from here, I think I want to show you example of applying random number in different level. This is highest level use of randomness. I mean, not the advanced anything, but that's the logically highest highest level random behavior. Meaning, most of the behavior below is regular. Only the highest level is irregular, which is this straight sequence of big square. Then, and the naturally next example would be going down a little bit in terms of level of application of randomness. And then let me show you example. First, copy and paste the code, and run the code, and then let me talk a little bit about the code. So now you see the randomness is applied here. Now it's checking clock number, clock level 2, which I didn't apply clock level 3. So previously it was applied to clock level 4, and clock level 3 was controlled here, which I didn't quite check. But clock level 2 is compared with random number, again random integer again, so somewhere between 3 to 10. Actually, this number y3 number y3 at 10. That's because I try many numbers and I like this best. So this level 2 clock is governing the length of sequence of square. So previously it was fixed number. I forgot what number. Maybe I don't know. So actually, I can just see the previous code. Previous code is this. Previously, clock number 2 or level 2 was 3. So it used to be 3 square to turn to create bigger square. But now it's 3 to 10 randomly. As a result, so at this edge, bigger edge, or length of sequence of square is somewhere between 3 to 10. Then you see that big square is now rectangular because it's checked not for all 4 edges, because it checks the randomness every edge or every sequence of square. So one, is there any extreme example? So for example, okay, for example, this one here, like a first stage. Okay, let me draw. So first edge is here, or first sequence. This is like 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe tens. So that's could be longest 10 square to create one sequence. And then next one is this, which is like 8, 2, 3, 4, 5, 6, 7. And then next is that. And actually, I think I counted it wrong. Or, no, actually, I didn't count it wrong. So usually, or so far, I think they are stopping at number 0, 1, 2, because usually it collides into the previous square. But when I was drawing this sequence of square, or square made out of sequence of square, I didn't tell to stop at 3 or 4 to make square. I just told it to keep going and then just stop when it collides something. So in this case, it didn't collide into the neighbor. So it kept going. So it was making square, but for them, it just making was keep going and turning 90 degrees and keep going until it collides. So in this case, kind of made a spiral of 90 degrees. So, but you can see each step is different length of sequence of square. So that's because of the this random number. So anyway, so that's logic. So that's the impact of applying the random number in this level, which is clock 2 level, third from bottom. And then as a whole, again, you still see they maintain 90-degree big grid behavior. And especially you see straight alignment at the center from top to bottom. That is because that was the first turn of this agent. And then I didn't, so like when it keep going, I randomized the length of sequence, but I didn't randomize angle or like when it's if sequence of big square is going, I didn't shift the location to branch. So this part is guaranteed to go straight still. But when it turns to left or right, again, it doesn't guarantee to turn in the same Y level. So it starts to shift the grid and sometimes it collides into something somewhere else and they create weird overlap of grid there. I mean, if this is the urban grid, that's a bit weird. It's a stitcher space. But anyway, so that's the logic of applying randomness into the middle level of logic of hierarchy. So, and next step, and then naturally it goes one level lower. So next randomness is, so that was a clock number 2 level randomness. The next one is, where do I have random number? Well, I might have multiple random. Wait. Okay. I have 2 randomness. This is just combining clock level 2 randomness and clock level 4 randomness, but as angle. So turning angle is random in the highest level. And then in the middle level, the branching behavior, well, actually turning, sequence of square turning behavior is random. So combine them together. So it's a combination of the highest level angle randomness and the middle level logical randomness, or actually length randomness. And let's see how it's gonna look. But I'm right now playing with randomness, and then but that is not the only way to search your design. I was just curious about this. Plus, that was one thing you can do. But one thing, one kind of important thing the complex system science suggested is that super regular logic can generate complex behavior. So although it's a quite difficult thing to do, um, but I mean, if you can achieve that, that you're kind of a genius to the level you find a strange attractor. But randomness is kind of an easier way to find kind of variation and diversity. Um, but in this case, I keep the coherence out of logic and then explore diversity out of randomness. So that's one way to do, although this is not only way. Anyway, so you see the result of um, middle level random sequence length combined with slightly off random angle. And then, but actually, this is something you can imagine. I mean, you can see how where is the random angle happening easy, and then you can see how where the middle level randomness happen. That creates this random size of a square or rectangle, and then yeah, you can see that weird angle. So that's that. So it's not that different or not dramatic, but just combination of randomness. And then next, this should be another randomness, and then which is okay. I have multiple random behavior again. So the bottom level 0 is same, just straight, and the highest level clock 4 has no randomness. So it's all happen in the middle level. So clock level 2 has randomness, although this is the same one with the previous one, meaning this would create a random uh, rectangle, kind of big size or middle size rectangle. And another thing is here, this happens not in the clock 2, but inside the condition clock 1. So clock level 1 random angle is this called. Um, so so combination of this, so this behavior we already saw. Actually, no, there is another one. Actually, clock level 0 also has behavior in terms of length. So level 0 is randomized. So it's base behavior, so it might have really kind of bigger impact, but the length angle is same, but the length is different. So bottom level H has random length, and then when they create the next sequence of not sequence, next square doesn't go straight. That has a random angle, which is this one. So I mean, still like each module, like a micro module is a line, but the second level module is a square or rectangle or 90-degree something. That part is kept, but stuff on top of that is randomized quite a bit. As a result, it's this. Then it looks very randomized because the randomness is introduced in a lower level, which has higher impact to the upper composition. So that's how it works. But you can still see kind of the highest level 90-degree turn is sort of kept, although not that clear. You see, for example, even though they are or like it's like you are navigating your ship, but your worker doesn't really follow your order kind of thing. But anyway, so this this part is still trying to branch into 3 directions, and the straight direction, and the left direction, and the right direction, and then they kind of it did turn or kept going or turn left and turn right, although it's the base angle is off, so that angle is also off, and then yeah, you made a 90-degree turn, but it's a, I mean, after that, we are going kind of wiggly way, and also other agent came into you and then collided into that, and you stop here, and then that this one goes straight. That was fine, but I think it also collided. Is that collision? No, actually, it's not collision. It's this one is still kind of try to create square, but it didn't quite make the square, and then but anyway, you know what I mean. So logically, logical structure is same, but bottom level length is randomized, and the medium level angle is randomized. Well, it's kind of lower level 2. So yeah, that's the result of that. And so that was the lower level randomization. And then I think I have another randomization. No, actually that was the last randomization logic. And then you can, actually that was kind of lowest in the example, but it's not the lowest you can do. And then lowest you can do is this guy, the straight line in the level 0. So if you randomize a line here, that will be the most randomized result. Let me just show you. Let me first go back to the most organized structure one and just change only the lowest angle. I mean, we already saw lowest angle non-random rotation, fixed rotation. But if you randomize the angle, well, how it would look. Although it might not be that, I mean, you saw the variation randomness so far, so I guess it's gonna be kind of similar vein, and I kind of try to imagine kind of okay, or okay range of angle to have some interesting results, but it might be interesting, it might be total chaos, I don't know. So, but anyway, you start to understand how, where you look at to change. Angle is one thing important, and then but when you set up this logic, building this if else and then clock, there is a level difference. If you change something in the higher level change happen, then lower level a big impact as a whole. So and then you might want to fine tune later. So that's the lowest level angle randomization. And then, I mean, as a whole, it's kind of, yeah, I think I have this example in the video I've shown in the presentation yesterday. But it's I mean, it's as a whole kind of an impression mentally might be close to this. But major difference is in zoom up condition, you can still see 90-degree rectangular thing. This one, plus this one didn't randomize the number of sequence or lengths of edge of square. That part is same. Only the angle of straight line is randomized. So you see kind of area-wise they are equal, and then you can see they are trying to make square room or whatever, just square geometry, and then you also see they are turning this big square 90-degree sort of, and but if you go far, you see they didn't go straight and collide into some other in a weird way. So sometimes kind of pentagon shape, sometimes square shape. Yeah, they are trying their best to. Actually, no, they don't care. They just follow the instruction. But yeah, so that's the result of change of randomization of this angle. So, but anyway, so just a technique of randomization. There's so many different way to apply, but actually it's just two major things. Applying each defined level is one thing, and then applying a random angle, actually a random angle in each defined level is another thing. So that's the thing. If you have 5 level, you can play with 5 level randomization in terms of clock timing, which usually defines like a number of sequence or length or repetition unit or module. And then that's one place you can apply. And then for the 5 level, you can have 5 different place to rotate different way to change the behavior. So that's one suggested process of design exploration with this algorithm. Okay, then it's been 1 hour in the afternoon. So I just keep going, and I think I have more. So from here, so I did from the beginning to here was just keeping example of square logic, and then from here I just show more kind of variation example. But maybe before that, I can go through the list of methods you can use as a thing, well, especially the one I didn't explain a little bit more advanced rotation. Although this doesn't show up until later example because those 3 rotation I have here is mostly about 3-dimensional transformation. I mean 3-dimensional rotation. And if you know 3D rotation well in like gaming, or if you use Unity, although actually not Unity use different system on Quaternion, but which is the like OpenGL, if you know how to code OpenGL, you kind of know this kind of thing, pitch and roll and roll, or if you somehow have the pilot license, you would know as well. So these are kind of usually flight navigation related way of 3-dimensional rotation. And so 3 different rotation means there is 3 axes to think about rotation angle. And then usually when we are thinking about kind of basic drawing world, our geometry is staying XY plane. And then when you use this rotation method with no axis input, that's XY plane. Although just note that this agent use locally defined coordinate system. So it's talking about locally defined XY plane, which might not be the same with XY plane, but global XY plane. But then that rotation is actually same with your rotation. Your angle is about the rotation angle on XY plane. And okay, so that this one is kind of easy to explain. And then 2 more things, pitch and roll. Pitch and roll is kind of easier. So okay, I think I should start right now to sketch something. But well, actually, if you Google and pitch your roll, actually that should be easier to show some diagram. Pitch your roll. So aircraft principal axis, that aircraft thing. So maybe I wanna see that. Hopefully this has good diagram. And so kind of vague. That's SVG file. Okay, so kind of that. So when you think about these 3 angles, you think of you being airplane, or at least you think about you facing front to somewhere. So this 3 angle is kind of relative angle based on your orientation when you have front direction and then up and side. So your is when you are standing and then looking in front, your rotation is XY plane is like a ground plane rotation. And but roll is around you. You're tilting your head around left and right is roll direction. And the pitch is about you looking up or down. So yeah. So that's a three rotation. And then this pitch and yaw and roll is the transformation like this. And each agent is like following this orientation instruction. So then they have local XYZ coordinate, and then that XYZ coordinate, like you can imagine each agent has a box, and they know which is up and which is left and which is front. So you can rotate that box. So although I'm not drawing box in the agent, so I mean you can if you want. Then so, but anyway, that's a kind of quick explanation of the three angle. And now I'm gonna demonstrate that in short, but I'm gonna answer some question on chat and then okay, explanation of next function one more time. So next function is basically equivalent to creating new child agent. So last time in the smart agent algorithm, or like all the assignment we are doing so far, was having, okay, let me show you or demonstrate. So, so right now this is like Kurok stack agent, right? Name of the class. So this was the way like we had position 2 and direction 2 or something. So we are doing this yesterday. And the next is just this short version of that. Although there's something I have to take care of, like how to set up the internal hierarchy of body clock, etc. So I kind of cover everything up with this next method. But you can just understand next means this. And also, yesterday we are doing like a direction to rotate something. That was happening inside. So actually, this could have done in the similar way yesterday. And so I'm doing this rotation, something rotation or multiplication is happening inside next method, but it doesn't need to be. But in the same way, when we are doing creating direction 2, this is just conceptual sketch of code. So when we are copying the direction to direction 2 and then rotate with some number and then put that into the child agent definition, we are doing this, but you could have done also something like when you write code like this, you have option to put everything inside the method. So here is exact same thing with this two line, and then that's put inside here. You could have written this way yesterday. This is shorter and quicker, but just more confusing, and that's why I didn't show that. But today we are doing the shorter, confusing way because I mean all other stuff is actually, I mean if it's because there's other confusing thing which is this logical structure, so I made it kind of short in here. So then plus 2 right first. So but anyway, so that this is equal conceptually to this. So that's what's happening, creating new child with transformation. I hope this explains better. Anyway, so I now go back to the rotation. So okay, so I have these three rotation method. So um, let me quickly show you that show you this example. And or actually, in this case, I want to go back to simpler behavior. I don't want to make the square of square. So let me just delete all stuff inside. Um, if you want to see this code, now I want to delete, but check the YouTube. So then I want to demonstrate pitch and roll and yaw. And first, so usually I just start with next, and then simplest is this, just going straight. And then, but if something happen, I want to turn. If clock 0 equals maybe 3, I want to turn. So I want to turn. So let me use your angle, which is actually exact same with rotation, so it's not that different. So I would put here like this, actually not like straight. But instead of this, I could use your, although this doesn't really matter if you use rotation or your angle because they are exactly the same. Then, but next I'm gonna show pitch. Something should be coming. Actually, but this gonna be the same. So I'm gonna start writing next code. Instead of you, what if I use pitch? So pitch is like looking up or down. So if I do that, this wouldn't stay on xy plane. This would be going upward in xy plane or downwards. But anyway, so you see this this down. That's the your angle. Then this is the xy plane. So I mean, it's flat. It's staying on xy plane. Then, but now instead I turn this on pitch direction. And I think positive angle on pitch would be going up, which I'm not sure. We will see when I simulate. Actually, that's a kind of attitude to make sure the number is working or not. Just run it to see if it's working. And so then naturally, I want to test the rolling angle next. So I want to start writing that. Okay. So yeah, on XY plane, nothing or it looks straight line, but in perspective view. So you see it's this one is staying XZ plane, but I'm still going. So but it lift or raise upward from here. So that's a pitch angle going up and going up and going up and coming back and kind of crashing into itself. But so that's pitch angle. And then roll angle is something tricky and interesting, or at least natural in terms of behavior of agent or this kind of agent. First of all, if I rotate this in this way, actually you don't, yeah, I'm gonna say this first. You don't see anything. You see only straight line because I'm drawing line. Rotating line around that axis of line doesn't change the shape of line. And you see the change only when you turn something. So what I'm gonna do is when I roll, I create another branch. First of all, yeah, this is just straight line. So then second, if I make branch on the right side means just rotating 90 degrees to the right. I'm not sure if I put number two or, but anyway, so actually I should have not done that because it's gonna confuse. I'm gonna keep this zero. So anyway, it's rolling gradient. But it's also branching 90 degree to the right, or not necessarily right, but I think that's a positive, actually positive rotation might be the other way, but turning to side direction 90 degree, but it's rolling itself. And you can see that's the rotation axis of the airplane from front to back. So you are tilting your head, or you are rotating your head, and okay, first of all, that's not what I was expecting. So let me change that. If that okay, if clock one. So what I'm doing is I had some logical error, so I'm changing that. Actually, I should have done this either. So this might branch too much, but um, so it rolls and it takes branch when clock one is one. Actually, I should have put clock zero is also zero something. And is that running? Something coming. Not sure this is working. Not quite working. So that level, I'm not sure if this works. So maybe I should pick some working example and change that. So I'm gonna go back. So, but anyway, so this is the kind of level of difficulty or complexity, a same level of my understanding. So although I made this code, then this one should be coming. Did it stop? I think they're colliding to itself somehow. So let me use this one. Actually, collision is a bit hell to figure out. I mean, self collision, especially you are turning something into something and you kind of don't know. So when nothing happens or something stops, most of the time your agent is colliding into each other. Then, then anyway, so let me see this one. I want to change the roll direction of this. And so this is level 0. Level 1 is, okay, first 9-step turn. When 9 is this, next sequence starts. This is the moment I want to change the roll angle. Then, so hopefully this works to demonstrate roll transformation. Okay, that should be coming. Yeah. Okay, so that's what I wanted to show. So you see, I mean, agent is going this way. I mean, the first action of some level of agent going this way, but I'm changing the rolling angle. So that rolling angle tilt the whole coordinate system or base plane of each local agent and or local base plane of each agent. And then, I mean, for each agent, they think they are drawing on their plane, but in global space, it's that plane is rotated. So that's a role. And so sideways angle. So anyway, that's a example or explanation of 3 rotation, pitch and yaw and roll. Although yaw is the same with regular rotation, and you can do exact same thing with just rotation with definition or with specific axis um, angle or angle vector. Although you will put some absolute vector which is not local thing. So yeah. Okay. Somebody's microphone is on. I think I can mute from here. Okay. If you intended to ask a question, I'll go ahead. Or you can type on chat, and I can either unmute you or answer the question. Anyway, so then next thing. So next I'm gonna just explain more stuff here, and then okay, I think I had a triangular example there. And before that, I'm gonna remind you the assignment part. Actually, I think I'm gonna talk about more about the research part. I already explained in the morning session about assignment. That there's 2 assignments. One is this agent work, this hierarchical agent work. So by just playing with those example and the changing number, changing logic, try to come up with something unique to yourself, and then or just trying to find something interesting for you, then submit that. I mean, submit, but just present that tomorrow in the beginning of the morning session. That's one thing. Another thing is to start thinking about your design project, which is also about building this code, this hierarchical agent code, but based on your research about existing geometric condition you find in, I mean, somewhere existing one. Like you can just Google search some interesting image, but specifically hierarchical geometry in nature or architecture or machine or anything, any image or any 3D thing. Either way, 2D is fine. Actually, staying in 2D world, just drawing world is totally fine, or painting, that's totally fine in this design expression or the final project of the workshop. But you can also do the 3D. I mean, but 3D is using this kind of 3D rotation or those kind of 3D operation. You can do that. I'm gonna show you how to build not only line, but some surface or sphere or box. Actually, it's gonna be still simple geometry for micro agent, because micro agent doesn't really create whole geometry that the composition or aggregation whole creates. So, but anyway, you can still make 3D surface example or on geometry. So you can choose 2D or 3D either way in your research part of assignment. So you're gonna also present that tomorrow, like what image you found and you are what part you are interested in. Then I hope okay, no, you also need to make diagram. Please make diagram of higher gradations. You can just make simple diagram suggesting what is the hierarchy relationship in the image you find. So that's the assignment. I kind of explained in detail, but anyway, the first part is just playing with this hierarchical or clock stack agent code to then demonstrate as your code tomorrow. So the example I'm gonna show for the rest of today is gonna be just could be based of your assignment example, and also of course for you to understand better about this agent for you to control to develop final project as well. So let me keep going. One more thing before that. When I said you can put surface in this example, what I meant is something like the video I've shown. So let me show on stop sometime. So this example I've shown is using surface as agent body. Not so currently in the example I'm showing just a line as a agent body, but this example shows surface, kind of square. So each square is, one agent. And then I'm gonna show you how to do that. Or I'm gonna just give you the example code of that, so you can use that. So, but there's tons of them. So in this case, because you're gonna have maybe tens of thousands of agents at the end, could be more. But meaning you would have micro agent geometry of that number, which will be a lot. So that's why each agent geometry should be simple if you build complex aggregation. So usually when you get million, the current level, usual typical computer cannot handle million surfaces. 100,000 of surfaces would be the maximum typically. But anyway, but anyways, I want to show you geometry options tomorrow. But today it's line. And then you don't need to pursue surface. You can stay line with color or something. Actually, coloration I might show tomorrow. Okay, then going back to example. I think I just choose some of the example and explain a little bit better about transformation and also logic. Okay, let me start with. Maybe start with simple. Okay, maybe triangular one. Just to explain, this is simple, but do I need to save this code? Yes, I do. So the example, the first non-square base example is about branching. So okay, I save this one and I'm gonna save another name. So the tutorial code on the web, just 5 lines is doing the logic of branching. We did branching yesterday. Then you kind of know. So branching was always about creating multiple child agent, and so next method is creating child agent. So having 2 of them means it is creating branching. So then that then turning angle is 1 is minus 30 degree, and then another is positive 120 degree. So that would show something here. Okay, it's kind of unclear, but if you zoom in the very first one, very first one is this, so it would be easier or to understand if I sketch. So first agent is this, and the first turning is this. This is a 30-degree turn, and that is a 120-degree turn. And then next one is like this is 30-degree turn, and this is 120-degree turn. If you do 2 y's or 120-degree turn, it forms a triangle. But anyway, so just but this is quite simple. You could have done this without hierarchical agent. It can be just a regular branching agent. So, uh, okay. Oh, this stops because my code has duration. Oh, no, it doesn't have duration. Um, I don't know why it stopped. Okay, so but anyway, so this oh, I hit the enter. Yes. So but anyway, but as a whole aggregation, you get this circular pattern which is coming from um, 30-degree turn. So 30-degree turn, and then it takes 12 time to form a circle. But main thing is that if you think about hierarchy, this small triangular thing actually, this Y shape is kind of module. Although this triangular thing is kind of module because you can see this as a thing round rotating sequence of triangle in a way, but you can also see the middle module is the round panel looking thing. It's a module, and then as a whole you start to form bigger aggregation. However, the reason why this is making whole is the same reason with the some of students assignments making fractal, and then there's a certain gap, certain regular pattern of collision and then gap happening, which is, we don't know. But if you really look into like mathematical analysis, you would find why, and you would get some formula representing this formation whole. But this is all about collision. Then collision is not all about space. Collision is all about space and timing. So when they are in the right time, right location, they collide each other and they cancel out and making this whole. So then the fractal shape you see in this algorithm is all made out in that way. Then anyway, and then yeah, so that's one example of branching. So you get, if you just put two agents next to each other, it becomes um, simple branching. Although this is not that simple because you see that one of them is branching into level 2 clock and another is branching into level 1 clock. So it's a different level of resetting. So that's the part why it's creating like a triangular module and then circular module. One of them making the circular module, another making the triangular module. That. And another thing, actually one example I want to talk about is this one. This is a method, transformation method I haven't explained yet, which is this flip normal method. So flip normal method is something you can guess from the name. It's flipping normal. But when you flip normal, your rotation, direction of your rotation flips as well, because when you say rotation, or when you use this rotation method, and then say you want to rotate 60 degree. I want to stop a bit. So, okay. When you switch or flip normal, and then, first of all, the behavior is you make two branches. One is rotating 60 degree, another is rotating 120 degree, which is, let me do that. Which is, so this is the first agent, and then this is 60 degree turn, and this is 120 degree turn. But for the second agent, which is, let me choose different color. For the second agent, that is this guy. This guy also turns 60 degree and 120 degree, but now it's turning other way, it's turning right. That is because you flip normal. So when you flip normal, the way it rotates it flips as well, because your z-axis going now down. So I mean in z direction, so negative z direction. So that's why this is kind of useful. So when you have, especially when you have like repetitive behavior, switching the rotation angle left to right or going one way, the other, every other timing. I mean, it doesn't need to be every other timing. You can use combining with the clock. So every 10 clock time in some level, you flip that, or you have one set of kind of modular aggregation, but you restart whole thing in flip way, you can use the flip normal, then they gonna go the other way. So that's one bit useful thing. And then I don't think you flip the side axis if you are using like a pitch and then roll. I think you only flip normal, not the side axis. That's I mean, in the world of mathematics or gaming, some computer system, graphic system allow you to have only like a left hand coordinate system, right hand coordinate system, something if you know what that is. Good, not if not, you don't you can ignore. But anyway, so I think this is creating. It is also switches the right hand system to left hand system. But anyway, this flips the rotation at least direction. Uh, without changing the rotation. So that's how this works. And that was an example of this, or point of example of this. Then, then let me move on to next example. And some more stuff which might be interesting. I mean, this one also has a flip normal, so it's kind. I mean, this is just rectangular thing. Scaling down with multiplication and the flip normal with multiplication. So I'm gonna skip, but I'm gonna just point out the flipping angle part, which is, so you see some of the square spiral or rectangular spiral is rotating one way, then other is rotating other way. That's because of the flipping normal. Then let me move to next. This one has a more 60-degree rotation logic, and it's more work. So this is like a hexagonal grid. Let me quickly show you. So this might be something similar to square of square logic, but this is like hexagon of hexagon. And it might be clean soon. So the level of, by the way, when you start like working on assignment and maybe pick some of the existing code from tutorial to start changing, you don't necessarily need to read code to understand. You can start just changing number. But if you start finding something interesting, maybe or you want to change in a specific, you should start reading. So, but yeah, you see like hexagonal or base hexagon is like this rotation. So this is spiral hexagon, and but this spiral hexagon is also kind of branched to another hexagon, and then the hexagon also create another hexagon. And I don't know what this spiral is, that side effect or something. So yeah, but you can see first of all, this spiral, actually this base hexagon spiral is not necessarily equal length hexagon. It's a kind of horizontal or elongated one. That's because I'm using different lengths of turn. One of them is 15. There might be another is 5. So the long edge is like first edge is like length 15, and the second edge is length 5, another one length 5. So if I make everything 15, that will create equal length hexagon, I guess. And then another one would be, actually one more thing I want to show, or I can kind of want to show how this one was originally hexagonal grid. Anyway, code is coming. Okay, question, can the pattern generate be projected onto single point surface? It's possible in the same logic with the last tutorial I showed yesterday. By the way, let me finish this one and answer the question. So this one, I just changed the length of the hexagon, and then the yeah, and then, but anyway, so the same logic is the original elongated hexagon, but I just changed the length of that, and then but that's a change. But this is still scaling down. By the way, I personally like this condition. Just happening accident. But anyway, so that's one thing. And then, but just okay, I want to show another thing is the spiral was called by scaling down. So if I don't scale down or multiply one, multiplying 0.99 is scaling down the length. If I don't do that, that wouldn't create spiral. Either putting one into multiplication, which does nothing, or I just delete multiplication, would not cause spiral. It just create hexagon. And so in the meantime, I could answer some question, but yeah, one thing I want to show is so running this agent system or hierarchy agent system on surface is possible by using the example I showed yesterday. And by the way, so I'm just showing the original hexagonal grid. So it was originally that, but it was scaled down and then spiraled down and then elongated to create this pattern. But anyway, so just logically same thing, but adjusting transformation, we create this. And then this one sometimes not showing the one edge in hexagon is because of the collision kind of thing, or they happen to be in same location, same time as they collide each other and cancel each other. So if you do want to create actual hexagon grid, that would be problem. There's a way to avoid that, but anyway. So just showing the relationship between these hexagons. So then now I want to answer the question. So if you want to project agent onto surface, it's possible using the same approach to this one. Multi-agent on the surface. I'm just pointing the direction, so I don't really explain in detail, and I don't exactly show how you can do in the code, but the concept is possible. But also I saw some of participants tried in our assignment, but it didn't work because there's a certain coordination is needed. Certain coordination is most of the time. First of all, the way this works is, let me show, not this one, but let me show this example. So this one, I mean, is on surface, but I think I have line open there. Just to sketch out the meaning of that, when you have some surface like like this. First of all, it needs to be single surface. You can cap single surface. If it's polysurface, it needs to be exploded. If that is not what you want, you have to rebuild single surface which resembles the form. And then, but anyway, so the way agent works is surface has UV local coordinate system. And then you can see, like, if you type the dir direction command, you see that direction, like kind of axis of u and v. The red is u direction, and v is red, yeah, green is v direction. Then you can see that, I mean, there's direction, meaning one of the corner is 0, 0 of uv. In this case, this part is 0, 0 in UV local coordinate. And it goes to like a 0.1, 0.2, and a 0.5 in the middle, and then in U value, and the V value is going up in vertical direction in this surface. So then that goes to 1, 1 here, not the way here. So that corner, the other corner coming back is 1, 1. So that's the local coordinate. Also, if you know where in Grasshopper, you do the operation after you reparameterize surface UV coordinate. Reparameterization is about reunitization of parameter number, meaning in actual line geometry, they have UV coordinate from 0 to 100 or 0 to 55 or negative 100 to positive 100. So you don't know if it's 0 to 1, but reparameterization makes everything from 0 to 1. In IGEO library, I forcefully reparameterize everything in the beginning. So everything is, all the surface is guaranteed to be 0 to 1. So what you need to do is, if you want to map agent, your agent has to run, actually I talked about this earlier, but your agent has to run between 0 to 1. So even when you want to have the agent running on the big surface, your agent needs to be staying here. If your agent goes out here, over here, it goes out of surface. So, but you need to design your agent to aggregate inside this area in a whatever interesting way you choose. So you have to be you have to adjust your size and then kind of make sure your agent doesn't go out or goes weird location, etc. And then you, okay, first of all, when you do that, you don't generate geometry here. Each agent generates geometry after you map your location onto surface. So anyway, so you need to make sure your agent is small enough to run around inside 0 to 1. Then inside 0 to 1, in the code, there's a part which is actually mapping. Actual mapping happens as a surface sample. When you have actually, when you have some location of agent between 0 to 1, you pick the XY coordinate and you use the UV coordinate of surface and you sample one point on surface to know where that is on surface. Then you use this point to create some geometry on surface. If it's surface, if we are creating like strip tree or some other geometry on surface, you need to sample many points to do. But that's a kind of basic idea. You run your agent inside tiny 0 to 1 square, then you convert your point to surface point to get some point on the surface and use that point to make geometry, line or surface or sphere or something. So that's how. Yeah. Then I mean, if you try that in your design project or final project, you can. I mean, for tomorrow, I don't think I can help in deep, but other than just over email. But like if you want to try on your final project, we have like 2 days of discrete tutorial, one on one session. So yeah, you can do that. I can show you more in more specifically. So that's one. And another thing, question or more like a comment about the memory usage of processing. And processing not that light, and then but Grasshopper is not that right. Actually, first of all, processing is one thing, and the IO library is another thing, and this agent is another thing. So this agent, but agent level is not that heavy, but geometry level kind of heavy. And then, but most important, let me show you most important thing about memory management in processing, which is processing has memory limit in default, not to crash your computer. So you can set or unset the limit by yourself. So in preference, there is that option, increase maximum available memory to that. So traditionally, that was quite limited to several gig or 2 gig or something in the 32-bit CPU days. But right now, most of the, I mean, I think your processing is now compatible to 64-bit, or you install. First of all, you should install 64-bit version of processing if you didn't. Although these days default is that, so I think you have that. And then in that case, you can increase the maximum memory to whatever memory chip you have. Also, of course, it doesn't use all of them, but you can increase that. So most of the time when you see the crash, if I keep running the agent for, I mean, complex agent, it's gonna crash. And then when it crashes, it's gonna show you red letter error message, and then showing the maximum memory something, and then couldn't do. So you can, first of all, you can increase that. Then I don't think increase that is too much might crash your computer. I don't know, but I'm running on this limit, and then so if you encounter problem, you can try that. You can try to increase this number. That's one thing, or kind of basic thing. First thing you can do. Another thing is that in IO doesn't necessarily consume memory more. Plus, agent itself is not that heavy. Heavy thing is geometry most of the time. So if you create point, it's super light. If you first of all, if you create nothing, you don't see anything but agent there, it's super light. Points light, line still kind of light. Sphere heavy, and then surface like a 4-corner point surface is heavier than line, but just double kind of. If you create a bit more complex like a strip around each agent, and you have 100,000 agents, yeah, that's getting the limit of use of memory, and then it's getting heavy. But another thing, so there's actually two or three things. Having geometry inside processing is heavy, but displaying that is another heaviness. It's a separate thing. So if you generate geometry, But if you don't show that in screen, you can still run more, which is kind of weird thing to do, although I sometimes do that. So when you are testing something and then at like 100,000 agent it crash, but I want to test 200,000, I kind of know it's gonna work. In that case, I don't show geometry, meaning that's kind of tricky. Yeah, actually, yeah, but anyway, so that's another thing. So, but anyway, most of the bugs that not showing but still generating is a bit tricky things to show in the code. So, so, but for you, maybe you can just, I mean, if you encounter that problem, I can show you how to. So, but anyway, so there's a several different level of memory management, and then if you are kind of staying rational in terms of like geometry management, etc. Especially in this tutorial or workshop, our focus is on the aggregation of the whole thing, like a composition of everything, and seeing how they kind of generate as a whole pattern. Meaning, we don't care the detail, we care the whole most of the time. We want to see the hierarchy relationship as a whole, and so you should not use too complicated geometry for each agent. You just should have simple agent geometry and then show bigger aggregation. So that's a basic attitude to it. So, but still, yeah, you could crash, and sometimes like a result design quality of 100,000 agent is different from design quality of million agent, which in that level you might need to do something like GPU acceleration, etc. Although there's still many things you can do before reaching there. So let's try that first. Then something in the comment about grasshopper, transferring grasshopper. This doesn't, I mean, IGO library can save geometry into Rhino, but grasshopper, not directly grasshopper, although somebody was writing IGO code in grasshopper and copy and paste it. That's different thing. Although, yeah, no, there's no direct way to do like exporting something from processing and IGO to grasshopper. Although, if any of you are expert in processing or coding or anything, or if any viewer on YouTube is an expert, one thing you can do, and sometimes I do, is I write code inside processing, which is grasshopper code or grasshopper Python code or something. So I don't generate agent, I generate code of agent. Actually, no. I generate code of geometry inside my simulation. Actually, not simulation, that's the case top down. And then I save the text file somewhere and containing 100,000 geometry, and then copy and paste in Grasshopper and execute that. It's possible to maintain some input parameter to adjust later. That's possible to do. I talk about this technique sometime, not in the presentation in the first day in this workshop, but I think I talk about it in other presentations, so you can find out, or if you have questions, ask me. Okay, then we are kind of reaching the time of today. Then let me wrap up by saying there might be something I wanted to talk, some certain method I wanted to show more in here, but the order list of method is kind of limited from here to here. So other stuff I didn't really talk about the reflection and the flipping. Reflection is just a 3D flipping. It's not that important. And the flipping tends to collide itself into your parent or something, but it's actually tricky to use. But flip normal is, I explained, you can use to switch the angle direction, and the flip side is actually flips that direction for pitching, I mean, pitch rotation. So kind of same idea with the flipping. So then, yeah, those. And this part I might explain tomorrow, or you might not use until the end. But anyway, so those are the options, and I'm gonna ask you to play with those code to generate something interesting for you, and of course for you to run, and then expect to see something interesting tomorrow. So just a reminder, assignment today's assignment is two things. One, first thing is to play with those code and generate interesting result. Yeah, you can check those example and play with that or any of that, and well, hopefully you can build your own. Then another assignment is to research existing geometry, like Google image search or something to find some interesting image using or interesting hierarchical geometry relationship. And then, I mean, for your as a reference of your final project, like a starting point to go, and then also make some quick diagram. It can be just simple, or you can just draw on top of the image, or you can even sketch on Zoom just to show this part seems to be module of this and sub module this, and this part seems to be have certain relationship to this, or this part and this part is kind of different module, etc. Like module A, module B, but the child module A, child module A, that kind of diagram. So I want you to show tomorrow or present tomorrow. So that's then maybe at the end of the final project, you might include a diagram in the animation if you edit your animation. So I think that's all. Unless you have any other question, I'm gonna finish today's session, and I'm still checking if there's something I should mention in the tutorial code. I think that's fine. Yeah, you can just test whole thing here, and then you can also change the color in the same way you did in the agent multi-agent algorithm. By the way, HSB is just kind of similar to CLR color RGB. This is just a HSB color variant, which means you can specify hue and saturation and brightness. So yeah. So anyway, okay, so I'm gonna finish today's session here, and then I'm gonna see you. By the way, when you play with color, you can use clock instead of ig.time. Okay, so I'm gonna see you tomorrow in the same time, same Zoom link, and also YouTube live. Tomorrow might be the last YouTube live, because after that we go into individual discrete tutorial session. So, but anyway, I'm gonna see you tomorrow, and then thank you for watching, and bye.